Hello, my name is Chungwei Tai and I come from Purdue University. I work with Dr. Vivek Narasimhan. Today we will talk about our research project on the theoretical study of cross-stream migration of non-spherical particles in the general second-order fluid. To begin with, particle in the channel flow can acquire lift forces due to several different mechanisms. For example, a deformable particle can interact with the channel and acquire lift force that can push the particle away from the wall. And this mechanism is also seen in a blood system where the red blood cell is deformable, and this will create a depletion layer red blood cell near the channel wall. For a rigid particle in the Newtonian flow with strong inertia, particle will migrate due to the inertial forces and form an annulus-like focusing pattern near the channel wall. When in a viscoelastic fluid, polymer in the fluid will establish a distribution of normal stress in the channel. Particles will feel the imbalance of this normal stress and migrate towards the region with the lowest normal stress differences, and that region typically corresponds to the flow center. In this talk, we will focus on the third mechanism and develop theory to describe particle motion in such a systems. Viscoelastic lift is very commonly seen in biological and industrial applications. In the field of microbiology, particle migration behavior can be used to analyze the rheological information of the suspending fluid. In oil industry, the hydraulic fracturing process uses particle suspension in viscoelastic fluid to crack open the rock layer and retrieve the oil. The efficiency of the process is highly related to the particle motion in the flow. This mechanism is also useful in developing label-free particle sorting devices such as viscoelastic cell cytometry or particle focuser for separating particles with different properties. There are many factors that affect the particle migration behavior in the flow. For example, particles with different size and shape can have very different migration behavior. In terms of fluidology, the intensity of the viscoelasticity, different flow profiles, and even shear thinning effect can have very strong impact on their migration behavior. In terms of channel design, the shape of the cross-section of the channel and also the curvature of the channel can provide us very different migration behaviors. Other factors such as the particle concentration and relative size of the particle with respect to the channel can greatly affect the migration dynamics of these particles. The major goal of this study is to develop theories and also experiments to understand how these factors will affect the migration behavior of the particles within the flow. In most real applications, particles are usually non-spherical, and however, in previous works, most people have studied the migration behavior of spherical particles in different fluids, but have limited knowledge on the effect of particle shape. In this work, we're going to specifically study how different particle shape will interact with flow and give us the different migration behavior of these particles. From here, we'll dive into a theory we developed in this work, but before we start, there are several important assumptions we have to make for our system. First, we'll assume the flow is incompressible and there's no shear thinning or thickening effect. We'll assume the flow has negligible inertia and is steady in terms of time. For the particle, we'll assume the particle is rigid and the particle shape can be arbitrary. And for our system, we'll assume there's no wall, and we're going to focus on the interaction between our particle and the flow profile. We set up system by flowing a particle in a general quadratic flow defined by this equation. And this quadratic flow consists of uniform, linear, and quadratic flow components. And here we use second-order fluid model to describe the fluid viscoelasticity, and this model is valid for any slow flow of weakly viscoelastic fluid. And there are two major contributions to the total stress. First is the Newtonian part, which is marked in blue here, which consists of the static pressure and the shear stress. And the viscoelastic part, that's marked in red here, which is the derivative of the velocity gradient up to second order. And there are several important factors for this model. The psi1 and psi2, which are the first and second normal stress coefficient that monitors the normal stress differences in the flow and shear direction for psi1 and shear vorticity direction for psi2. And alpha is the ratio of psi2 to psi1, which tells us the relative intensity of psi1 and psi2. And here we use Weisselmann number to characterize the overall viscoelasticity intensity, which is defined based on psi1. And the major goal of this work is to develop a way to analyze the motion of a force and torque-free particle within a quadratic flow of second-order fluid. And in other words, we have to calculate the polymer force and torque on the particle, and we have to balance the force and torque by the Newtonian counterpart to analyze the particle trajectory within the flow. As you can see from the second-order fluid model, the equations are nonlinear and the solution process might not be that straightforward. To approach this problem, in our previous work we studied a special case where psi1 is equal to negative psi2. In this case, the viscoelasticity only modified the fluid pressure and the fluid motion is still the same as Stokes flow. One big advantage of this assumption is that we can derive an exact solution for the polymer force and torque on the particle. The exact solution consists of elements from two major groups. One is the element from the external flow, such as the velocity gradient and vorticity. The other one is the force moment in Stokes flow, such as the Newtonian force and torque on the particle, which depends on particle shape and orientation. This model is applicable to any particle shape in an arbitrary flow profile up to quadratic order, and this model provides a qualitative prediction on the particle dynamics within the flow. For most real viscoelastic fluids, alpha is typically not negative 1/2, and it will be necessary for us to go to more general case to get a more quantitative idea on the particle dynamics within the flow. So for this study, we're going to focus on the case where psi1 is not equal to negative psi2. In this case, the viscoelasticity will modify the shear stress, and there's no exact solution available for the polymer force and torque on the particle. To approach this problem, we'll apply perturbation expansion analysis based on small Weismann number to retrieve the first order correction on the particle dynamics. And for simplicity, we'll only focus on the dynamics of the spherical particles, such as polar and oblate particles within the flow. For the perturbation expansion analysis, we'll first define the disturbance velocity, pressure, and stress field of the fluid based on the external field. We'll then expand the disturbance field on a small Weismann number and calculate the solution at different orders. We'll truncate the solution at second order and focus on the solution to the first two orders. First, for the zeroth order problem, this is simply a Stokes flow problem, and we can easily solve for the fluid velocity and calculate the particle translational and rotational velocity at this order. For the problem at order Weismann number, the system is more complicated due to the contribution from the viscoelasticity. In this case, the fluid motion is pretty difficult to solve, and we therefore apply the Lorentz reciprocal theorem to help us bypass this problem and directly solve for the velocity correction at this order. With the information above, we can calculate the total particle velocity and to analyze the particle motion within the flow. In this study, we'll focus on the motion of two different types of spheroids. For a spherical particle, we only need two characteristic lengths to describe their particle shape. A polar particle can be derived from stretching from a sphere and has one longer axis and two equal shorter axes. An oblate particle just the opposite and has one shorter axis and two longer equal axes. All the particles studied here will have the same total volume, and their geometry is defined based on the equation shown up here. Here we use particle aspect ratio, AR, to characterize their asphericity. We define the particle orientation based on the direction of their axis of symmetry. There are two angles we'll specifically discuss in this work. For a system with flow in x direction and shear in y direction, we define the phi angle to be the angle between x direction and the projection of the particle direction onto the xy plane. We define theta angle to be the angle between the particle axis and the vorticity direction, which is the z direction in our system. In this talk, we'll specifically discuss the particle motion in a 2D quadratic flow in x direction with shear gradient direction in y direction. There are several questions we'd like to answer. First, how does the normal stress ratio alpha affect the particle migration velocity and also the rotational dynamics? And secondly, how does the geometry and orientation of particle affects their mobility within the flow? And third, we'd like to know what's the overall migration orientation trajectory of the particle within the flow. And finally, we'll compare the result of this model to our previous work under the Corotational limit. First, we'll examine how the normal stress ratio affects the particle migration behavior in the flow. For most viscoelastic fluids, we'll have positive psi1 and negative psi2, and the magnitude of psi1 is typically way larger than psi2, and alpha therefore falls between negative 1 and 0. Different types of viscoelastic fluid can have very different normal stress response. For a dilute polymer solution, alpha typically falls between negative 0.2 and 0, and for a concentrated suspension of Brownian particle, alpha can go up to negative 0.9. And in this work, we'll examine the different alpha value from 0 to negative 0.9 and see how it changes particle migration in the flow. The first thing we'd like to see is how alpha will change the migration velocity of the particle in the flow. In this plot, we show the particle migration velocity at different theta angle and at different alpha values. We see that in terms of different angles, the two particles show opposite trend in respect to theta in migration velocity simply due to the geometry definition, and we'll discuss about this in later slides. In addition, for all the tested angles, particle shows the same trend with respect to alpha in migration velocity, and will have higher migration velocity at higher magnitude of alpha. Next, we'll look at the angular velocity in terms of theta and phi angle at different alpha values. In this plot, we show the angular velocity theta dot and phi dot at different orientations and at different alpha values. From these four plots, we see for both particles, alpha has very little effect on the particle angular velocity. The difference in angular velocity at different alphas is less than 2% for both particles. Based on these data, we can conclude that normal stress ratio alpha has very significant effect on particle migration velocity, but surprisingly has very negligible effect on particle rotational dynamics. Next, we'd like to know how the particle geometry and orientation will affect the particle mobility within the flow. We'll understand this by this scaling theory. A particle is migrating due to the polymer force, and the polymer force is balanced by the Stokes drag. Based on the previous study, polymer force is scaled as the volume times the gradient in normal stress. For the case of a 2D stiff flow, this can be simplified to a gradient in just y direction. On the other hand, the Stokes drag is scaled as the viscosity times the radius of the particle and also the velocity of the particle. If we balance these two forces, we can get this scaling derivation for the migration velocity. The velocity is proportional to Weismann number, square of the particle size, and also the distance of the particle from the flow center. And the MD here is the mobility coefficient, and this depends on the particle geometry and orientation. Next, we'll plot the particle mobility data at different particle aspect ratio. One interesting thing we saw here is that if we define the quantity LSG to be the length the particle spans in the shear gradient direction, in this case will be y direction, and if we plot the mobility data with respect to this LSG quantity, we see that for both particles, the data will collapse onto one major curve. For the case of theta at equal 90 degree, both particles will have their longer axis available for LSG, and in this case, if we increase the particle aspect ratio, we'll see both particles have higher mobility due to the longer LSG. On the other hand, if we have theta equals 0 degree, the LSG for the polar particle will now become the shorter axis, but for oblate particle is still the longer axis. In this case, if we increase the particle aspect ratio, we'll now see the oblate particle will still have the higher mobility, but polar particle will now have lower mobility simply due to the shrinking shorter axis. Another thing we saw is that particle mobility is also proportional to the alpha value, and the proportionality is approximately linear. From this information, we can conclude that, first, particle mobility is proportional to the length span in the shear gradient direction, and the mobility coefficient scales linearly with the normal stress ratio. Finally, we would like to see the overall migration and orientation trajectory of the particles. We release the particle at halfway from the flow center and monitor their position and orientation with respect to time. From the migration trajectory, we see that in general, oblate particle will have faster migration than polar particle, and spherical particle has the fastest migration among all the particles. This behavior can be explained by their orientation trajectory. In this plot of the theta trajectory, we see that polar particle and oblate particle have very different orientation behavior. Polar particle tend to go to theta equals 0 degree, which we call a log rolling state, and oblate particle tend to go to theta equals 90 degree, which we call a tumbling state. In addition, both particles show a fast transition of theta angle towards their favorite orientation in the early stage of the migration, and they spend most of the time in that orientation during their migration. Due to this behavior, we'll have the LSG for the polar particle to be the shorter axis, and therefore the slowest migration, and oblate particle to be interchanging between the shorter and longer axis and have faster migration than polar particle. We know that this trend in migration velocity is also maintained for different particle aspect ratio, and for the effect of alpha, higher magnitude of the alpha simply provides faster migration velocity of the particle towards the flow center. Lastly, we'll compare the general second order wave model to the Corotational limit model. From the results of this study, we see that the normal stress ratio alpha merely modifies the migration velocity but not the rotational dynamics. In our previous study, the results from the Corotational limit model are qualitatively consistent with this general model. Since in general, the full numerical evaluation process for the general second order wave model can be quite computationally intensive, we therefore can apply the exact model to get a quick evaluation of the qualitative behaviors of particle within the flow. In conclusion, we have developed a theory based on the general second order wave model to investigate the migration behavior of spherical particles in 2D flow. We see that the normal stress ratio alpha has strong effect on the migration velocity, but not on the rotational dynamics. The overall migration behavior is the result of the interaction between fluid rheology, particle geometry, and orientation. Particle migration speed is proportional to the magnitude of alpha, and LSG governs the particle mobility, and particle orientation will change the LSG and gives the particle different migration speed. And finally, the Corotational limit model can capture the essential physics, and we are able to use it to do a quick evaluation of particle dynamics within the flow. With that, I'd like to thank my advisor Dr. Vivian Nottingham and also Dr. Xiang Wang for the collaboration. We'd also like to thank Dr. Arzu Adekani and Dr. Sangtae Kim for the insightful discussion on this project. We finally would like to acknowledge the financial support from the ACS Petroleum Research Fund. Thank you for your attention. We have our Q&A session on November 19th at 8 a.m. to 9 a.m. Pacific Time or 11 a.m. to 12 a.m. Eastern Time.